In 1967, Ford Motor Company produced the GT40 Mk1, one of the most remarkable pieces of Ford racing history. In 1999, Ford once again revisited the concept of the GT40. This video will demonstrate how a designer's idea evolves from exceptional concept renderings into clay and digital models, and finally, a full-size model. A program description and customer profile outlined by design management determines the size and type of vehicle to be developed. This direction is forwarded to the respective design team who begin sketching. These sketches span all levels of ideation and concept development, sometimes scribbled on a notepad or even a napkin. But most begin in the computer, using a paint box software that facilitates the designer in creating a two-dimensional rendering. The paint program can simulate markers, pens, or airbrushes, offering the designer an unlimited palette of traditional rendering tools, allowing them to define and express their unique vision of the vehicle. The design team reviews and critiques these sketches, deciding on the images with the best appeal and potential. Of the 100 initial sketches, the field is narrowed to the most exciting and feasible designs appropriate for that program's DNA. Now, the computer-aided industrial design, or CADE, process begins. The two-dimensional sketches are transferred to the Alias or Auto Studio 3D design software. This enables easy revision of surfaces and details to the model. The designers create and refine the surfaces and can produce photorealistic renderings and animations to evaluate design attitude or surface quality even before the model begins its life in clay. These sequential images or animations are invaluable resources and give scientifically accurate reflections, refractions, and shadows. The photorealistic animations allow program team members to see the state of the math data in a matter of days as opposed to weeks or months. Using the BunkSpeed software application, designers can view their surfaces in a dynamic environment with realistic changing reflections. This is an improvement over previous software which only allowed for static or snapshot imaging. The resulting surface math data from the 3D design software is constantly shared with engineering so they can package the vehicle and identify feasibility issues. Packaging defines the spatial constraints, such as headroom, legroom, and visibility, which are critical in designing the interiors and exteriors of the vehicles. Using the math data created in Alias, the design program moves into the next phase, the translation of the 3D dimensional data into the clay model. Design Systems receives the package information and exterior surface information necessary to generate an aluminum and steel understructure support of the armature. The primary piece of the armature is the frame. The armature will travel to the wood shop where craftsmen will outfit it with wood to be used as the base. The frame is moved to the plastic department for foam to be glued and screwed into the wood-clad armature and made ready for digital math modeling and milling in the numerical control department. The foam is oversized and it must be milled back 2 inches under the scanned surface. Once the foam milling is complete, the armature is delivered to the design studio where modelers apply clay over the foam. The clay must be applied in layers and cooled very slowly. This provides a good, solid, workable surface for the 5-axis torus mill to cut using the selected Alias surfaces from the CADE design process. The full-size model is evaluated after the first milling. Design management decides which areas need to be readdressed. Proportions, stance, front view, rear view, and side profiles are all evaluated together to understand the designer's intent. The design can be further developed using the Alias software in the computer, or the team can elect to make changes by hand, with the modeler sculpting the clay to fine-tune the surfaces before being scanned back into the computer. This scanned information can be used to duplicate the model from one side to the other and to continue the design development. Based on the design team's direction, other exterior items such as bumpers, headlights, grills, taillights, hardware, and ornamentation are developed. Much of this is done concurrently in order to include these items on the clay model. At the same time, color and materials designers are concentrating on detail components. Trim panels, instrumentation, seat design, bumpers, and body materials, and colors are just some of the elements that have to be coordinated in order to achieve a total vehicle. After the design improvements to the clay model are completed, it is time to add color to the model. Most clay models are routinely covered in a silver-colored material called die-knock. This is a decal material consisting of 3 layers: a decal, glue, and paper. The silver die-knock is used for management reviews. The silver shows contours most effectively and is a neutral color for evaluation purposes. Once the clay is evaluated and approved, plastic molds are made from the clay model to create a full-size fiberglass model. The fiberglass model will now be fitted to the appropriate chassis and painted. The full-size model then receives the cosmetic components such as mirrors, windows, wheels, headlamps, tail lamps, and moldings to make it complete. Some full-size models will be equipped with an interior and have functioning doors, while others are strictly exterior models. The new vehicle is now available for management reviews and photography sessions. It requires the combined efforts of the interior, exterior, and color designers, clay modelers and math modelers, along with the wood, metal, and fiberglass fabricators to turn a vision into a reality. If this model is to become a production vehicle, the math data and packaging information is forwarded to the manufacturing engineers to complete the product development process.